All right, so today we're going to try and conclude the chapter 1 lesson on electricity. All right, so what we've done so far is we've talked about a few different things. We talked about volts, amps, and ohms. Also showed you Ohm's law. And then you also utilized a meter to read voltage, which you should have done to complete 5 different objects. 6 different objects, really, but one you read in 2 different areas, like the relay coil and the contacts. So what did you get for number 1? For the incandescent lamp that was cold, how much resistance was in for problem number 1?
18 ohms.
18?
17.7.
Oh.
That's with it. That's the cold light. 19.7. 17. Okay, we'll just go ahead. I got 16.3, but we'll go ahead and we'll say 17. Make sure you put the ohm symbol on there too. All right. So you might have had 16, 16.3, 17. Okay. So look, for number 1, this is a resistive load. There's going to be 3 different types. Resistive load. All right. So let me tell you, Ohm's law will work for a resistive load. So if I gave the power 120 volts, using the EIR over here, what would the current flow through the wire be, or our amps? So how would you find that? In other words, if I clip the amp probe around that wire, it should match up with the number that I get from using these 2 numbers with Ohm's law. So you got the E, that's 120 volts, and you divide it by our R, which would be what? What's your math there? You got your calculator out. Get your calculator real quick. 120 divided by 17. 7.05. That seems like a lot for some reason, but we'll go ahead and we'll move on. All right, so we got another one. What about the cold lamp or the hot lamp? This one was cold. What happened to the resistance when the value went high? When the lamp went hot? It went up to what? What's your number that you got for the hot one? How much?
21.9.
All right, so it went up to 21 ohms. What type of load is that? It's a light bulb. So there's a resistive load, an inductive load, and a capacitive load. What type of load is a light bulb? What was number 1? What did you write down next to number 1? All right, and then what's number 2? What's number 1? Name that for me. What does it say next to number 1? Incandescent light bulb. That's right. It's not a compact fluorescent. It's not one of these tubes. It's not an LED light. It's a regular filament light bulb. Incandescent light. Regular light. Regular old bulb from back when Edison started the light. And then what's number 2 then? Incandescent lamp. Same thing. So if number 1 is a resistive load, what do you think number 2 is? Resistive load. Same thing. And then, does that produce heat, those lights? Those incandescent lights?
Yeah.
So it's kind of similar to number 3, which is what? What did you get for number 3?
11.5.
How much?
11.5.
I don't know, my reading, but my meter looked like the battery, somebody left it on. So 11.5, what? Ohms. Anybody else get a different number? My meter read like 30 ohms. But let's say that heating element's going to get supplied 240 volts. What would the current draw be on that? Using Ohm's law. So now you got 240 volts supplied to 11.5 ohm resistor.
20.8.
20.8? That sounds about right. 20, we'll go with 20 amps. All right. And what kind of load is that? It's just like the light bulbs, right? Yeah, resistive. Yep, so number 3 right next to it. How many watts would this pull? How can I figure out watts? What do we do to figure out watts? Because it's not on this wheel. I got another wheel to show you, but it's not on this one. I times V. I times V. So what's I? What's another word for I? Nah, well, okay, so intensity. All right, so we're going to take the amps, and what are you going to do with it? No, the volts. So what is that? 240 times 20? How many watts is this?
6,800.
You sure?
4,000.
240 times 20?
Oh, accent.
How much?
4,800.
4,800 watts. Or I could say it like this. We're probably not going to say 4,800 watts. I could say, how many watts are in a kilo? How many are in a kilo, period? 1,000. So I could break this down to where it says instead of 4.8 watts, I could write it 4.8 kilowatts. Actually, that was a 5 kilowatt heater. So the 5 kilowatt heater, when it's supplied with 240 volts, will draw a current of 20 amps through the wire. So you got to make sure you're running the white wire, because this 20 amp wire, it's got to be a little bit thicker than the number 14 wire that you're using for the light bulbs up here, right? What changed? Well, the wattage almost looks like it would think that the resistance value is lower, but the voltage is higher. So it's sort of like that heating element I showed you when we're heating it up. All right, it's going to glow a little bit. And then what happens when the resistance is too low? Like say I kept the voltage the same, right? And you saw that one heater, it was able to come on and eventually took about a minute or so to glow when you saw that heater. But what happened when I changed the heater size to like something, what do we use? The what? The spiral notebook. Spiral notebook heater coil was not as long as the dryer heater coil. So when I applied the same voltage to it, it heated up a lot quicker. The current went up, and then it glowed real fast, and it burnt the wire. It broke the connection before anything more could happen. Also caught the paper on fire, which was kind of cool. But that spiral coil, so I kept the voltage the same, but I lowered the resistance, and it didn't last as long. It overheated real quick. Same thing's going to happen with your electrical wire. If you use the wrong size wire for the amount of current flowing through it, that wire is going to heat up just like that. Only it won't be as dramatic and it won't be as quick, but it will catch on fire and it will burn the house down. So you got to make sure you're using the right size wire when you're doing all your projects. And for just a single light bulb, that number 14 is fine. In fact, you could hook 4 or 5 light bulbs in series, well, parallel, but you could hook 4 or 5 light bulbs all to the same circuit, and it'd still be fine. So the ones that run through the kitchen in your house, what do you got plugged in your kitchen? Refrigerator. That's going to draw a lot of power, more than a light. Oven. All right, the oven's on its own separate 240 circuit if it's electric. If it's gas, it's something different. Microwave, yes, that's got to be on its own circuit too. Because if you have the refrigerator and the microwave pulls 10 amps, refrigerator pulls 10 amps, that's 20 amps right there. It's going to trip the breaker every time you try and run both at the same time. The refrigerator, so they each got to be on their own circuit. And then there's another 20 amp circuit that's got to go around for all the counter plugs. What do you got plugged on the counter? Tell me all the stuff that you think you got on a counter. Coffee maker, that's a big heating element. Toaster, that's another heating element. Dishwasher, that's another thing too. It's got a heating element and a pump for the water. A little mini oven, yep, you got one of the little toaster ovens, a little pizza oven, something like that. Blenders sometimes are on there, that's a motor too, pretty much the same thing. So all these loads that are in the kitchen have got to have a higher current rating on their wire compared to the other ones throughout the rest of the house. Because of this Ohm's law, because of the way it works out. All right, so let's move forward a little bit more. Number 4, the relay coil. We're not going to use the Ohm's law with the relay coil because now we switched it from a resistive load to an inductive load. This is going to be like it creates a magnet, an electromagnet. I don't think the eraser's working too hot on the smart board, or the computer's a little slow. So what'd you get for number 4, the relay coil? How many ohms was the relay coil? 11 ohms. I got about 10, but that's right. So you got 11 ohms, and we can't use Ohm's law because that's going to be an inductive load. Inductive load. Okay? So that's going to be a little different, and I'll show you why with Ohm's law a little later. The contacts, number 5. So you read the relay coil, and then you had to read across the contacts. What were across the contacts reading? Not 0. 0 is good. 0 means you got no resistance and a complete connection. Did you have 0? What does it say on the meter? No.
I got 0.09.
No. Should have got nothing. Should have got OL. The meter should have never said nothing but open link. Or an infinity reading. Alright? An infinity reading. Like that. Anybody ever seen that crazy 8 symbol before?
Yeah.
That is the same thing as what we have on our meters now. It's OL. Open link. It means it's never making contact. That contact is like the switch being off. Right? Switch was off, contact wasn't closed, so that meter should have just read OL, open link, all the way through it. And then you had the fan motor down on the bottom. This is not anything. Inductive, capacitive, this is just a switch. That's a control, all right? So that the contacts are a switch. The last one, number 6, the fan motor, what'd you get for that?
48.4.
That's pretty good. I got about 47, 48, so that's the same thing. All right, so that was that. So bam, you got that there. So now you got to use on the back. Everybody turn over the back page and hold it up. You should have done that the day I was gone from the sub. Let me see it.
I wasn't there.
Uh-huh. No, not good. So now we got to do it now. All right, so look, Ohm's law. I showed you one wheel. One wheel had just EIR, but we also can incorporate power, or expressed as watts. This is the way I just showed you, a simple way of finding it. You take the volts, you times the amps, that lets you know what the watts is, okay? But if you don't have the volts and the amps, you might have resistance or amps. You can do it another way. We don't need to memorize this particular wheel, because I can show you a way that you can do it if you just had the EIR to still calculate for power, all right? Providing you got 2 of the 3. So, but the wheel gets bigger because they're adding power to it. And now they're going to start using the square roots or the squares to find out some of the stuff. So look on the back of your page. You were given on number 6, find the power, find the voltage when you were given the power of 1,000 watts and the current is 8 amps. So what are we trying to find, EIR or P? What is voltage?
Oh, E.
E. Okay, so we're trying to find E. And which ones are you given? Watts, which is what? Power. All right, so you're given 1,000 here, power. And then what else were you given? Amps. All right, so 8 amps. So it's 1,000 divided by 8. What do you get for that? 1,000 divided by 8.
125.
So the first one for number 6 is 125 volts. See how you found that? You just plugged in the number to the wheel. So what's number 7? Do number 7, because you can do it a couple different ways. You got to find the resistance. So that's going to be, I'll do this one in red, R, over here. What are you given?
Power.
You're given your power,
60.
and
Voltage is 12.
the voltage is 12. So voltage is going to be, which one of these are you going to use?
The one on the left.
Which one of these are you going to use? 1, 2, or 3? 3. So you're given power, and you're given intensity, amps. You're given amps.
Oh, bad. Did you see the?
Okay, which one are you going to use? 1, 2, or 3? P and E. So you got P and E. So that's it right there. So what's your E? 12. And what are you going to do with it? Square it, and then divide that by what?
960.
960, which will give you what? Where's your calculator? You need your calculators out. Can't you tell we're doing the math? Everybody should have their calculators out.
It's 0.15.
0.15. Yeah, it's nice to wait around for the other people to do the math, but that's not going to let you learn. 0.15 amp. 0.15 amps. All right? I'm sorry, 0.15 ohms. Resistance. I'm already on to the next one. So number 8. What are you given? You're given power and what? And you're trying to find what? Current. Which one's current? P-E-I-R? Alright. And what do we have? Power and voltage, which is this one here. So it's going to be power, 500. It's kind of hard to read that. I'm going to go back to green up here. 500 divided by what?
50.
50 gives us 10 amps. Alright. And then the last one is sort of like what we just did with the heater element. You got to try and find the wattage when the resistance is 24 ohms. So we're back up over to here, trying to find the power wattage. And you're given current. So you're given current and resistance right here. So your current is going to be 10 squared times your resistance value of 24, which gives you what? 10 times 10 is 100 times 24 is 2,400 watts. Or what else could I say?
2.4 kilowatts.
2.4 kilowatts. Right, yep. Y'all seen Back to the Future, right? 4.5 gigawatt. No, that's one of the best lines. All right, so, okay, last one. I'm going to show you 2 ways to do the last one. Do it on your own, and then I'll show you 2 different ways. See if you can do the number 10 on your own. You're looking for power, so that's going to be the P. You're given voltage, and you're given resistance. Now, with voltage and resistance, you can find amps. So you can do this, and then this, or you can just do one of these right in here and do it with one less step. So I'll give you a minute for that. So you got to find power when the voltage is 200 and the resistance, and don't say nothing until we get it all together. I see some pencils still writing, so we'll do it together. I'm going to erase some of the others while you're waiting. Alright, so one way I could have done it, I see some of you done, is I could have taken 200, squared it, and divided that by 400, right? So that's using pretty much this formula over here, because we got the voltage and the resistance. Or, you could have done this. If you wanted to just use EIR, you could have taken the E, which was 200, and divided it by the 400, which gives you what? 0.5. So that's how much amperage was flowing through the wire. So now that you know the amperage of 0.5, you multiply that by the voltage, which was 200, and that's going to give you 100 watts, right? Same thing here. 200 squared is what? 200 times 200? 40,000. 4,000 or 40,000? 40? And then you take the 40,000 and you divide it by 400, and what'd you get?
100.
Same thing. 2 ways of doing it. One was using EIR and just switching it around because you had all that stuff to do EIR, right? And then the other way is just using this pi formula that expands for power. All right. Bottom line is, we can use the Ohm's law. We're not going to use it that much as far as with it looking like this, but you will see it like that again on a test. So you need to make sure that you got it down as far as just plugging in the numbers. Resistance. You don't need to write all this down. But you got to have opposition to flow in the circuit. If you take the black wire and you connect it up right to the white wire and there's no resistance, some of you will see this yourself with your project when you don't test it before I get to check it, and you just plug it in and you got one wire connected from the black right to the white, boom, spark. No load. Needs a load. Whether the load's a big load like the heating element from the dryer or a smaller load like the coil that we had on the spiral notebook, it's got to have a load. It's got to have opposition. We measure that opposition in ohms, all right? And it's got to have some resistance and provide the path for those electrons to flow through it. So think about the space of a bridge going across a gorge, all right, or a river or something like that. So think about the cars as being the electrons flowing through the wire, and the bridge is going to be our load. So let's say, boom. Right now, it's like the switch is off. It's open. There's infinite resistance, or else it would show also, some meters will show the actual crazy 8. Others will just say open link, something like that. So but there's no way for these cars to get from this side to this side over here. So what are we going to do? We're going to add a load. And the load's going to be just a small path for the electrons to flow through it. Could be like our light bulb. So boom, we get a little load in there. Now we can get the electrons to move from one side to the other. And if I wanted more current flow, what could I do to the load?
Add another bridge.
Add another bridge, add another load. Yes, or increase the load. So if I get less resistance because we've added more load, and that's going to cause more cars to be able to travel from one side of the bridge to the other. Now, what happens if I add, you're thinking, well, why don't we just add a bridge all the way across? What would happen to this cars over here if we added a bridge all the way across and they all want to park right here? It's going to be a mess. It's going to be a big old traffic jam. So think about this. You got to have, the resistance can't be too much. And the resistance can't be too little. It's got to be just right. You got to have just the right amount of resistance for the current to flow so it doesn't get out of control. Boom. That's it. Done deal. Overload. So that's what they call an overload. When you're taking it, hopefully there's a fuse or a breaker that will trip. In fact, that was the word of the day, breaker. It's just sensing that heat, that current flowing through it. And when there's too much current flowing through because the load is too low, it trips the safety back in your box to say, no more power. That's it. Shut it down. Resistance, watts, and amps. A couple other things. The load's going to affect your amps and your watts. All right, so the bigger the load, something happens with the amps and the watts. When you lower the resistance, the amps and the watts go up. When you increase the resistance, the amps and the watts go down. So it's going to be a direct relationship. Take a look here. Draw this out. You got L1, L2. Draw your little things. You're going to draw your resistors looking like a Charlie Brown. When it's open, there's nothing. No amps. There's no current flow through a wire. There's nothing. You're going to have to draw all 5 of them. Now, I got a 1500 ohm resistor. It's going to be 10 watts of power. I could use the Ohms law to figure all this out. And then as I lower the resistance, what's going to happen to the amps and the watts? So I lower it down to 150 here. What happened to the amps and the watts? They increased. Keep going. No. You got to finish this up with me. Bell-to-bell instruction here. And then when you got no resistance, boom! That's it for resistance and loads. Okay, that's it for chapter 1. Next we're going to be talking about series and parallel circuits. And then I have to talk about AC/DC power. If you saw the shocker video, you'll be getting shocked come Wednesday.